All right, let's get started today with chapter 7. Okay, we're moving on to a new section, chapter 7 today, which is, as a reminder, not going to be covered on the next midterm. So this, starting today, will be material that's exclusively going to be covered on the third midterm and the final. So you won't have to worry about this next week. But we are going to keep moving forward, and we're going to start today with some topics related to energy, work, and heat. All right. So in chapters 5 and 6, we talked about changes in matter that occur during a chemical reaction, how reactions change in the product, how to classify different types of chemical reactions in terms of the types of changes that are happening, how to calculate masses and moles and all kinds of things for reactants and products. Now, the other part of a chemical change that we're going to start talking about in chapter 7 is the change in energy that occurs during some physical processes and also during chemical reactions, which is the more important part for us. So we talked about this a little bit in chapter 3. So if you think back to several weeks ago, or towards the beginning of the semester, we talked about bond energies and how we can use bond energies to estimate the change in energy when reactants convert into a product just by summing the bond energies on the reactants and product side and subtracting them. So we've been introduced to this a little bit, and today we're going to talk in more detail and start talking about more detail about energy and how it relates to chemical processes. So first we need to define some very basic things. All right, so energy, there's a lot of definitions for it, but the one that's going to be relevant to this course is energy is the capacity to do work. And we'll define work in more detail in a second. But the basic idea here is that for energy, we have two different forms of energy that are going to comprise any system. We have kinetic energy and potential energy. Kinetic energy is energy due to motion. All right, so we should be aware of what kinetic energy is, but for chemical reactions, the kinetic energy part is not particularly important because typically the reactants and the products have very similar motions associated with them. So we're not really going to be changing the kinetic energy a whole lot during a chemical reaction. So this is a topic for physics courses. If you take those, you'll see that all the time. But we're really going to mostly deal ourselves with potential energy. Now, the general definition for potential energy is it's energy due to position or composition. And particularly the second part here, energy due to composition, that's the aspect of potential energy that's important for chemical reactions. So the different bond strengths that you have in different chemical compounds is going to give them different chemical potential energy. And then as you do a chemical reaction and change one thing into another, you're going to change the chemical potential energy that's associated with that. And that's what gives rise then to the change in energy for the reaction. Now there's this thing that you're going to learn probably in more detail about in chemistry too, and possibly in physics courses, called the laws of thermodynamics. The first law of thermodynamics tells us that the first law of thermodynamics tells us that the energy of the universe is constant. So in other words, that you're never going to create or destroy energy, but we can have change in energy if we define what's called a system and its surroundings. So when we're studying change in energies, we have to isolate some part of the universe that's going to be our system. So the system is the part of the universe that we're studying. If we studied the energy change for the entire universe, it would always be zero, according to the first law of thermodynamics. But if we want to study a chemical reaction, we have to define some part of the universe that we're going to focus on. And then for the purpose of a chemist or a chemistry course like we're in, The system is usually going to be an enclosed container of a substance or a chemical reaction. So if we're measuring energies associated with physical changes, again, we won't see a lot of that in this chapter, but things like taking a gas and compressing it, or changing the state of matter from solid to liquid to gas, something we'll see a little bit later on in this semester. If we're measuring energy change associated with that, we need a closed container of that substance that we're going to measure the energy that flows into or out of that closed system. And very often the system is going to be defined as a chemical reaction itself. So the reactants and products in a chemical reaction is going to be the system, and then we're going to measure whether the energy increases or decreases for that system as the chemical reaction takes place. And then the surroundings is going to be everything else in the universe that is not part of the system. So when we're measuring energy changes, what we're really measuring is flow of energy from the system to the surroundings, or from the surroundings to the system. So there's no overall increase or decrease in energy for the whole universe, but we are measuring how energy transports from the system to the surroundings, or vice versa. And that's what we talk about when we're measuring energy changes for a chemical reaction or for a physical process. So if energy is going to be transferred between the system and the surroundings, there's two ways that can happen. When we transfer energy, we're going to have some change in energy for the system, delta E, which is equal to the final energy minus the initial. So anytime we see delta, we've seen this in a few other contexts, delta means final minus initial. We've seen delta E in the context of the Bohr equation for atomic energy changes. When we're talking about the change in energy for a system, it's just the final minus the initial. And there are two ways that energy can change. There are two ways that energy can either enter the system or leave the system to the surroundings. And those are called heat and work. So heat is often known as thermal energy. And it's energy that's transferred as a result of temperature differences. So if your system and your surroundings have two different temperatures and they're in contact with each other, there will be energy transfer in the form of heat. And this one is fairly intuitive. There can be, if you take a red hot piece of metal and drop it into a glass of water, you're going to see the energy, the heat transfer between them, where the water is going to warm up a little bit and the piece of metal is going to cool down. So this one is pretty intuitive. You put a piece of ice cube, if you put an ice cube on this table, it's eventually going to melt because heat from the surroundings are going to go into the ice cube and raise its temperature. So that's what we mean when we're talking about heat. And then the other form of energy is work, which is not something we're going to deal a lot with in this course, but we will see a little bit of this today. And that's all other forms of energy transfer. It's called work. And it usually involves an object being moved by a force. All right, so we have two forms of energy transfer, heat and work. And then if we want to calculate or measure the change in energy for a system, it's going to be the sum of these two, the heat and the work. So we add the two together, and that gives us the change in energy. So the first equation we're going to deal with, which is a very simple one, is delta E is equal to Q plus W, where Q is the heat and W is the work. So anytime there's a change in energy, there's going to be some combination of heat and work that are involved in that change in energy. and the sum of the two is going to give you what that change in energy is. So the first thing we need to understand before we start learning different ways of calculating Q and W is we need to understand the sign conventions. When is heat positive or negative? When is work positive or negative? And then what does that mean about the sign of delta E? All right, so let's think about a situation when heat is positive. What does that mean? That means that heat is absorbed by the system. So all of these signs are relative to the system. We're always studying change energy for the system, not for the surroundings. So when heat is absorbed by the system, that means Q is positive. That means the heat is coming in from the surroundings into the system. And then if we have a positive work term, that means work is being done on the system. So if we're doing something to the system, doing work on the system, either moving it or raising it to a different height, whatever the case is, that's going to be a positive work term. And if we have Q and W are both positive, then the delta E has to be positive. That means you're going to have an increase in internal energy. All right, so whenever heat and work are both positive, that means you have a positive delta E. And then we can have sort of the other extreme, which is if both heat and work are negative. So a negative heat means that heat is released by the system. So that means heat is flowing from the system to the surroundings. That gives us a negative value for Q. And then if we want a negative work term, that means work is done by the system. So if the system is what's doing the work, that means it has a negative W term. And then if you have both negative Q and negative W, that means delta E has to be negative, which means the internal energy decreases. But then we can also have situations where there's energy transfer between the system and the surroundings where Q and W have opposite signs. So if we have a negative work term, which means work done by the system, but then we couple that with a positive value of Q, which means heat is absorbed. Change the color, keep them consistent. So if heat is positive, the system is absorbing heat, but then it is also doing work at the same time, then the sign of delta E depends on the magnitude of Q and W. So it can be either positive or negative. All right, and then the last possibility, last combination is if you have positive work, which means the work is being done on the system, but at the same time the system is releasing heat. Then you have the same situation where the sign of delta E depends on the magnitude of Q and W. It could be positive or negative, depending on which one of those terms is bigger. All right, so the first things to understand about heat and work are whether it's positive or negative. And that means for heat, heat is absorbed. That means it's positive Q. Heat released is negative. For work, if the system is doing work, that's a negative W term. If the system is having work done on it, it's positive. And then the sign of delta E. A positive delta E means that the system is gaining energy, it's increasing its internal energy. A negative delta E means it's losing energy, or that its internal energy is going down. And then depending on the combinations of Q and W that you can have both positive and negative delta E's. Okay, so that's the first thing to think about. Now another concept that's important for us to start introducing is this idea of a state function and path independence. So what is a state function? The simplest definition of this, which doesn't really define it but allows us to at least identify what a state function is it's anything with a delta in front of it. So we've seen delta E now, and we'll see some other things that have deltas. Anything with delta in front of it is a state function. And whenever we have a state function, what that really means is that the value of that only depends on the final and initial states. It doesn't matter how we got from the initial to the final state. So for delta E or any other state function, the value only depends on the starting and the final conditions. And this gives rise to the idea of path independence, which is that if we're calculating delta E, we don't really care how it gets from one point to the other. All we care about is where it starts and where it ends. That is going to give us the same delta E value. There's infinite numbers of ways to get there. So let's look at two possibilities here, just as a hypothetical. Let's say our initial state, we don't typically measure the absolute energy, but let's say we can in this case. And let's say our initial state has an energy of 10 joules. Joules is going to be the unit for energy. And then let's say it changes to a final state that has an energy of 20 joules. So to calculate delta E, it's just the final energy 20 minus the initial, which is 10, which is going to be plus 10 joules. Okay, so our delta E only depends on this initial and final state, and there's a number of ways that we can get there. So let's suppose that our path from our initial state to our final state, we can do it in a couple different ways, or actually infinite different ways, but let's talk about this possibility. Let's say we do plus 30 joules of work. So we do work on the system, 30 joules. That brings it to a value of 40 joules. And then let's say in a second step we do minus 20 joules of heat. So the system loses 20 joules of heat. Delta E is Q plus W, which is 30 minus 20, which is still plus 10 joules. So this is one way that we can achieve this change in energy. We do 30 joules of work on the system, and then we lose 20 joules of heat simultaneously or in a second step, and that gives us to this same final state. But we could also do the opposite. We could say, let's lose 20 joules of heat first. That takes us to an energy of minus 10 joules. But then if we do plus 30 joules of work on the system after that, delta E is still Q plus W, which is plus 10 joules. All right, so a state function is anything where the value of that only depends on the initial and final states, and there are infinite numbers of ways we can get there. The value of delta E will be the same. So whether we do work and then heat, or they do heat and then work, or any number of combinations of values of Q and W, the value of delta E is not going to depend on that. So that's what we call a state function, which is a path-independent function. There's an infinite number of ways to get from the initial to the final state, but the value doesn't change no matter how we get there. Q and W themselves are not state functions. They don't have delta in front of them. So the value of Q depends on how the heat transfer takes place. The value of W depends on the type of work that we're doing or how it gets from the initial state to the final state. So Q and W themselves are not state functions. When you add them together, you get delta E, which is. So that's just a little conceptual point, not too terribly important, but we do want to understand a little bit about what it means to be path independent and to have a state function. But now let's start getting into a little bit more of the practical stuff. So we have work and heat. Let's learn about how to calculate them for different systems. Work we're not going to deal a lot with. This is going to be the only type of work that we talk about, and it's really the only type that's particularly relevant to chemistry anyway, and that's called expansion work. Now the book goes in kind of an unfortunate order because we'll start talking about gases in the next chapter, but expansion work is a topic dealing with changes involving gases. So we need to understand a little bit about them, and we'll see more of that in chapter 8, so this will start to make even more sense by then. But for a gas, one of the parameters that you can use to define a gas is what's called the pressure. So the pressure is the force divided by the area. So if you have a container of gas, the gas molecules are all moving around and they're pushing on the walls of that container, and the pressure is the force of the gas divided by the area of the container that is pushing against. And the units that we're going to use most often in this course are what are called atmospheres. And so atmospheres is essentially the pressure of the atmosphere at sea level. So that's the unit that we use for pressure. We'll see a lot more about this in chapter 8, so we're just going to introduce it briefly here. But the one thing we should be able to do now in this section of the course is calculate work for a gas as it changes its volume. So the equation is that the work is equal to the negative of the external pressure times the change in volume. So the external pressure, P external, is going to be a constant pressure that the gas is pushing against, or that is pushing on the gas. And then delta V is going to be the change in volume. So if we have a container of a gas and it changes its volume from one value to another, the work that that gas does is given by the external pressure, the pressure on the outside of the container, times the change in volume that the gas undergoes. The most common units for pressure and volume are liters and atmospheres. So when we multiply these two together, we get a product that has the units atmospheres times liters. That's not really the energy unit that we're interested in. So for work, heat, energy, we're always going to be wanting to be in joules. So we have to use this conversion, which is 1 atmosphere times liters is 101.3 joules. All right, so once we multiply the pressure and the change in volume together, we have to then convert the answer to joules by using this conversion factor. So if we think about the signs for this process here, if our final volume is bigger than our initial volume, so that's one possibility, that means our gas is expanding. And so that means the change in volume is going to be positive, greater than 0. The volume is getting bigger, which means that the work, since we have a negative sign in this equation, is going to be less than 0. We have a negative work term. Remember that negative work means the work is done by the system. So when a gas expands against a constant pressure, when it increases its volume, that means the gas is doing work, the system is doing work. And then the other possibility is if we have our final volume is smaller than our initial volume, that means the gas is going to be compressed. The change in volume is going to be negative. That means the work is going to be positive because of the negative sign in the equation. And that means work is done on the system. All right, so anytime a gas changes volume, there's going to be work involved. If the volume of the gas gets bigger, that means the gas itself is doing work. If the volume of the gas gets smaller, that means the system is doing work on the gas. Those are the two possibilities. So that's really the only type of work that we're going to have to calculate. So let's just see one example of how we do this. So let's say we have a reaction at constant temperature and it produces a gas, and the volume expands from 1 liter to 10 liter against a constant pressure of 0.978 atmospheres. So a picture of this is that this black line here is sort of the movable ceiling of our container. The gas starts out at a volume of 1 liter, and then during the chemical reaction it expands and it ends up with a final volume of 10 liters. And we want to know what's the work done by the gas during this process. All right, so like I said, there's only one simple equation that we have to know how to use for this. The work is going to be negative P external times the change in volume, delta V. So our constant external pressure, this is the only type we're going to be dealing with, is negative 0.978 atmospheres. So that's the external pressure that the gas is expanding against. And then the change in volume, delta V, is, remember, final minus initial, anytime you see delta. So the final volume after the reaction is 10 liters. And then the initial volume, this is 10.00, if we want to be precise with significant figures. If we care. 10.00 liters. The initial volume where we started is 1 liter. So it's changing its volume from 1 liter to 10 liters, which is a change of 9.00 liters. So negative P external times delta V, we get minus 8.80 liter atmospheres. And remember, this is a non-standard unit for work or for energy, so you have to convert that into joules then. We have minus 8.80 liter atmospheres, and then the conversion that I gave you is 101.3 joules for every liter atmosphere. That's going to be minus 891 joules. So you're basically multiplying it by 100, a little bit different than 100, but minus 891 joules. So that means that this gas is doing 891 joules of work when it expands from 1 liter up to 10 liters. And that's the only type of work we're going to be dealing with. I don't know if you cover this in chemistry too, but there are other situations where if the external pressure is changing or the external pressure is not constant, you can calculate work in different ways, but this is the only one we have to be able to do in this course. Constant external pressure, you multiply that by the change in volume, and that gives you the work for the system. All right, so that's expansion work. Now we're going to introduce a new topic or a new state function called enthalpy. The idea here is that if we want to, as we saw, if we want to measure delta E for any process, we need to measure the heat and the work. So we have to measure, two processes. So that's, a little bit inconvenient to have to do that every time, measuring both Q and W independently to get delta E. So, and the reality is that most reactions in the lab are done at constant pressure. So we can define a new state function that allows us to just measure heat and allow that to then relate to that state function. So our change in energy is Q plus W. And remember that if we have a constant pressure, if we're doing the reaction at a constant pressure, whatever process we're talking about, the work is going to be minus P external delta V, which if the pressure is constant, we can just rewrite as minus P delta V. There's only one pressure to worry about if it's constant. And then if we're measuring heat at that constant pressure, we can abbreviate that QP. So we'll see later on also QV, which is heat measured at constant volume. But if we're measuring the heat and the pressure is constant, we can just abbreviate that QP to tell us that it's at constant pressure. So at constant pressure, we can rewrite delta E as QP minus P delta V. So that's the form of delta E whenever the pressure is constant. And then what we can do is we can solve for QP, because in a laboratory setting, measuring the heat is pretty straightforward. Measuring the work term is not always as easy, and we don't want to have to measure both of them. So if we just solve for QP, QP is delta E plus P delta V. It's a sum of two state functions. Delta E and P delta V are both state functions in this case if the pressure is constant. And then we can rewrite that as a new state function, delta H. All right, and so then the key equation here is that delta H is equal to QP. So this is a much more convenient state function for us to measure when we're talking about chemical reactions, because it doesn't involve heat and work, it just involves measuring heat. All right, so H is what we call enthalpy. You'll see a lot more about enthalpy in chemistry too as well, so this is an important topic for both this semester and next if you're in this chemistry sequence for the long haul. And so H is E plus PV. If we just take out the deltas, that's what we get. And so this delta H then is a new state function, which is just the heat measured at constant pressure. It's equal to that. All right, so if we measure the heat at constant pressure, that directly gives us this new state function delta H, which is related to the change in energy but is defined slightly differently. All right, so most of what we're going to be talking about in chemistry is going to be dealing with delta H, because most chemical reactions are conducted at constant pressure, and in most cases it's easier to just measure the heat as opposed to measuring the heat and the work, which is what you need to be able to do to calculate delta E. All right, so we have this new state function delta H. Let's see how delta H and delta E compare to each other. So I'm kind of setting you up with the idea that, well, delta H is a more convenient state function that we can measure. It's easier to get at than delta E, but is it at all, anything related to delta E? So remember that the definition of delta H is delta E plus P delta V. So how do these two state functions differ from each other under different conditions? So if we have a chemical reaction that doesn't involve a gas, we talked a lot about aqueous reactions in the last chapter, so that would be an example of a chemical reaction where there's no gases involved. In these cases, we have very small volume changes. All right, if you've ever mixed an acid or a base together, you don't see the volume changing drastically when that happens, right? It's just you add the two things together and they react, but no change in volume. So anytime you're doing a reaction that's in the solid phase or in the liquid phase or in solution, you're not typically going to have very large changes in volume, which means that this P delta V term is very small, very close to zero. Because if the volume is not changing during a chemical reaction, delta V is close to zero, P delta V is approximately zero, which means that in this situation, delta H and delta E are almost identical. All right, so this further underscores the convenience and the importance of delta H is that for many chemical reactions, like the ones that we mostly do, which are in solution, delta H and delta E are almost identical. So just by measuring the heat at constant pressure, by measuring delta H, we have a pretty good approximation of the change in energy for the system anyway, because they're really not that different from each other. Now, there can also be reactions that involve gases, and this is something that we'll talk a lot about in Chapter 8. But let's say that the moles of gas do not change during a chemical reaction. So let's say we react hydrogen and chlorine, and we make 2 HCl. So if we look at the reactants and the products for this reaction, there are a total of 2 moles of gas on the reaction side, 1 H2 and 1 Cl2. And then on the product side, there are also 2 moles of gas, 2 moles of HCl in this case. So if the number of moles of gas is the same on the reaction and the product side, that also gives us a P delta V term that is equal to 0. Something we'll learn more about in Chapter 8 is that the number of moles and the volume, those are all related to each other. So if we're not changing the number of moles of gas in our system from reactants to products, the change in volume will also be 0. And in this case, delta H is rigorously equal to delta E. And then finally, if we talk about a gas phase reaction where the number of moles of gas does change, so let's say we take carbon monoxide and react it with O2. So 2 gases that are reacting to make CO2, another gas. So in this situation, we have 3 moles of gas on the reactant side, 2 CO2s and 1 O2. We only have 2 moles of gas on the product side, 2 CO2s, so the number of moles of gas is changing. And so in this case, that P delta V term is not going to be equal to 0. It's going to be a non-zero, which means that delta H is not equal to delta E. All right, because we now have this non-zero P delta V term that we have to add on to delta E to get delta H. However, that said, for most chemical reactions, this P delta V term, this work term that we have associated with delta E, is going to be much smaller than the heat change, QP. Which means that even for these reactions, in almost every case, delta H and delta E are pretty similar to each other. There's not a huge difference between delta H and delta E. All right? So really what this is trying to convince you then is that delta H and delta E are not all that different from each other in terms of their magnitude, in terms of their value. And delta H is a much more convenient one to measure because it just depends on the heat measured at constant pressure, and we don't have to worry about the work term itself. So delta H and delta E are fairly similar in terms of their value, but we do want to be aware of the precise difference in their definition. All right, so now that we have this new state function delta H can be either positive or negative, just like delta E, and that introduces new terminology called exothermic and endothermic. So for an exothermic reaction, QP, which is equal to delta H, is less than 0. So the value of delta H, if it's less than 0, we call that an exothermic reaction. And that means that heat is released from the reaction as a product. Now heat is not really a product of the reaction, but you can think about it in that terms. As the chemical reaction takes place, heat is also produced in addition to the products. So if heat is a product, for example, if we burn water, sorry, not burn water, we can't burn water. If we burn hydrogen to make water, 2H2 plus O2. So if you've ever set a match to hydrogen, you know that it rapidly catches on fire, and it's a pretty dangerous thing to do in large quantities, obviously. The Hindenburg is one example of that. But anyway, we can burn hydrogen to make water, which can occur in the gas phase. We should know that this generates a lot of heat, right? As I said, when you set hydrogen on fire, it releases a lot of heat. So that means we're going to have sort of heat formed as a product of this reaction, and this would be an exothermic product. And when you have an exothermic reaction, or any exothermic process, the temperature of the surroundings increases. All right, and maybe people that have spent their whole life in Texas aren't familiar with these things, but another example of this are these heat packs. If you ever go skiing or other people use these, they keep their hands warm, these hand warmers. There's a chemical reaction that takes place in there. It's an exothermic reaction. It's releasing heat, and that's what causes the packet to warm up. So whenever you have an exothermic chemical reaction, the temperature of the surroundings increases. And then we have the opposite process, the opposite case when we have an endothermic reaction. So for an endothermic reaction, QP is equal to delta H, and it's going to be greater than 0, which means that heat is absorbed by the system. And in the context of a chemical reaction, can be thought of as a reactant. Endothermic reactions are less common than exothermic for reasons you'll learn about in Chem 2. But one example isn't really a chemical reaction, but if we dissolve ammonium nitrate, if you have the opportunity to do this, it's kind of fun. You dissolve this in water, and you have to add heat to this for this to work. So basically, when you dissolve ammonium nitrate in water, the solution feels colder because heat is going into the system from the surroundings. And an application of this are these cold packs, which the ones that don't require you to put them in the freezer, but where you just break open something inside of a little bag, and then all of a sudden it gets really cold for you. That's going to be an endothermic reaction where the temperature of the surroundings decreases when that happens. All right, so exothermic delta H is less than 0, endothermic delta H is greater than 0, and the temperature of the surroundings either increases or decreases depending on whether those are endothermic or exothermic. So look at this in a slightly different way. We can look at these enthalpy diagrams. So let's say we have enthalpy increasing from bottom to top here. Let's look at the case where we have an exothermic reaction. That's going to be the one here on the left. So for an exothermic reaction, that means that delta H is less than 0. That means the reactants have more enthalpy than the products. So if enthalpy is decreasing, that means the enthalpy of the reactants is higher than the products. And then the heat from this reaction is going to leave the system. So whenever we have an exothermic reaction, heat is released from the system, and that causes the temperature of the surroundings to increase. And then we have the opposite story for an endothermic reaction. For an endothermic reaction, delta H is greater than 0. That means the enthalpy of the initial state, which is the reactants, is going to be lower than the enthalpy of the final state, which is products. So during an endothermic reaction, the enthalpy is increasing, delta H is greater than 0, and heat is going to flow into the system during the chemical reaction, which is why the temperature of the surroundings then gets lower, because the heat is flowing in from the surroundings into the system. All right, so this is just a slightly different pictorial way of talking about exactly what I said in the last slide, the difference between an exothermic and an endothermic reaction, which relates to the sign of delta H and then also to whether heat is flowing into or out of the reaction. All right, so that's some ideas about delta H, which we know is related then to the heat. So how exactly do we measure that heat change, or that heat that's flowing between the system and the surroundings? So now the last thing we're going to do today is talk about an equation that allows us to calculate heat. All right, so let's think about some hypotheticals for a second here. So let's say we want to heat up some water to a certain temperature, okay, on the stove. If we put just a little glass of water on the stove, or if we put a huge pot of water, which one would you think would require more heat, the small one or the big one? All right, most people said big. Few people said small. So think about it. If you're trying to take water to a certain temperature, you're going to have to put more heat and from whichever one has more water. The more water you have, the more heat. So the heat that you have to put into a system is proportional to the mass. So when we're calculating heat, it's proportional to the amount of mass that we have. And then let's say we want to take the same pot of water. One of them we want to heat it up to 50 degrees Celsius, and then one of them we want to heat it up all the way to the boiling point, 100 degrees Celsius. Which one requires more heat? The one with the higher temperature or the lower temperature? Higher temperature. So the higher the temperature, the higher we want to raise the temperature, the more heat that has to be involved as well. So heat is also proportional to the change in temperature. So remember that this little sign here, this little alpha means proportional to. And then the common math trick that we use in chemistry is that heat is proportional to two things. It's proportional to the mass and it's proportional to the change in temperature. So that means heat is also proportional to the product of those two things, mass times the change in temperature. And then if we want to make this an equality, we just have to put a constant in there. So to change a proportionality into an equality, into an equation, we put Q is equal to the mass times C, this is our constant, times delta T. Okay? So this is the famous heat equation, MC delta T, where the specific heat capacity, which is abbreviated C, is the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius. So the value of C that we use depends on what substance the heat is either flowing into or out of, but it's the amount of heat that's needed to raise the temperature by 1 degree Celsius for 1 gram of that substance. Now, a part that becomes a little bit confusing in this section is that if we're talking about delta T, we're talking about a difference between two temperatures, the difference between two Celsius temperatures and the difference between the corresponding Kelvin temperatures is the same. So when we're talking about delta T, we can think about it in terms of Celsius or Kelvin. And that's because of the size of the degree for Celsius and Kelvin is the same. So a temperature change of 5 degrees Celsius is the same in magnitude as a temperature change of 5 Kelvin. The absolute temperatures are not the same, but if you're talking about a difference between two temperatures, whether you use Celsius or Kelvin, that delta T is going to be the same value. So don't be confused by that. That's something that I'll sort of use interchangeably as we go through this. The only specific heat capacity that you should memorize, the one that you're going to use all the time in this course, is that for water. So this specific heat capacity, C, is depending on the substance that you're talking about. And for water, C is going to be 4.184 joules per gram Kelvin, or you can also write that as gram degree Celsius, because again, the change in temperature is the same whether you're talking about Celsius or Kelvin. So this means that to raise 1 gram of water by 1 degree Celsius, you have to put in 4.184 joules. And so then if you want to calculate the heat change or the heat flowing into and out of water for a different amount, you have to need to know the mass and you need to know what the change in temperature is. And the product of those three terms, MC delta T, will tell you then the amount of heat that either went into the water or out of the water. Okay? And then another related concept, but one that we're not going to use very much, is molar heat capacity. So if we have specific heat capacity is for 1 gram of substance, molar heat capacity is for 1 mole. We won't use this one very much at all, but we should be familiar with it. And this is the amount of heat needed to raise the temperature of 1 mole of substance by 1 degree Celsius. And whoever invented the heat equations was just absolutely ruthless when it came to abbreviations. They're terrible. So the abbreviation for molar heat capacity is also C. There's a capital C, not a lowercase c. Don't worry about that too much, but we'll see we have specific heat capacity, we have molar heat capacity. Later on we'll talk about something called total heat capacity. All of them are basically abbreviated C, so you just need to know the context to know which one you're actually using. So if we want to calculate the molar heat capacity for water, we can do that pretty simply using the specific heat capacity. So the specific heat capacity for water is 4.184. Remember that the units for that are joules per gram Kelvin. And if we want to convert grams into moles, remember we can just use the molar mass. So for water, there are 18.02 grams in 1 mole. And so the molar heat capacity for water is 75.40 joules per mole Kelvin. So it takes 75.4 joules to raise the temperature of 1 mole of water by 1 Kelvin or 1 degree Celsius. So we won't use molar heat capacity a lot, but you should be able to at least calculate it or at least understand what it is. So let's just do a couple examples of determining the amount of heat involved in a physical or chemical change. All right, we're gonna use this equation a lot in the next few lectures as well. So we'll just learn it here and then see how we apply it in more detail in the near future. So let's say we do an aqueous chemical reaction in 50 milliliters of water, and we see that the temperature raises from 22.31 degrees Celsius up to 28.37 degrees Celsius. So the temperature is increasing. Determine the heat absorbed by the water. All right, so Q is equal to mc delta T. We're talking about the heat that's absorbed by the water, so we need the mass of water, we need the specific heat for water, and we need its change in temperature. All right, so we have 3 terms here. The specific heat capacity is a constant, which will sometimes give you, sometimes not, but I'll try to put it in all the test questions at least, but at any rate, you should remember that one. But we need the mass and we need the change in temperature. So here's another part that's going to come up in this chapter a lot. We're conducting the reaction in 50 milliliters of water, but the equation really needs the mass of water, not the volume. But remember that the density of water is 1. So anytime we have 50 milliliters of water, the density is 1 gram per milliliter. And so the mass of water is also going to be 50 grams. So when we're doing these types of problems where technically we need the mass of water, mass and milliliters are more or less interchangeable because the density of water is 1. So we have 50 grams of water. The specific heat capacity for water is 4.184 that we just introduced. And now we need the change in temperature, which is going to be T final minus T initial. So anytime you see delta, that's final minus initial. So the change in temperature, our final temperature is 28.37. Our initial temperature, we're told, is 22.31. So the difference, the change in temperature is 6.06 degrees Celsius, which, remember, for a delta T, for a change in temperature only, that's equivalent to the change in temperature in Kelvin, however we want to think about it. Delta T is the same in degrees Celsius or Kelvin. Because if we were to convert each of these individual temperatures into Kelvin and then subtract them, we would still get a difference of 6.06, because to convert from Celsius to Kelvin, you just add 273 to each one. So when you're talking about a change in temperature, it doesn't matter whether you use Celsius or Kelvin, it's going to be 6.06. So grams cancels out, Kelvin cancels out, and then we get an answer in joules, which is 1268. Very often in these problems we'll specify a unit, which is often going to be kilojoules. So we divide by 1,000 to get 1.27 kilojoules. We can specify the units here, but heat changes are more often going to be done in kilojoules as opposed to joules. Okay? So that's going to be how we calculate Q for water raising its temperature. I'll do this last one in the notes, but this is really the same thing, same equation. We're just solving for specific heat instead. So Q equals mc delta T. We solve for the specific heat. I'll go through that in the notes, and you can try this one on your own. All right, I'll see you guys on Friday, where we'll have both class and the exam review at 3 p.m. afterwards.